Good evening, everyone. I hope I'm audible. Just a yes or no would be good in the chat, or you can unmute yourself. Hello, am I audible? Yes. Thank you, Roshni. Okay. So, uh, welcome everyone to the problem solving session to the course Thermodynamics. And in this session, we will be primarily dealing with the concepts that were discussed by Professor Anand in the lecture videos, and then we will just try to solve some relevant problems to your assignments that would be quite helpful for you to understand the course in a better way, as well as help you to build up the concepts to uh, understand the course in a better way, and maybe deal with the exams that after the end of this course, and maybe other competitive exams as well. Okay, so I think I will just slowly go through the concepts that were discussed in the class by Professor Anand, and then after a brief discussion of the concepts, we will directly go on to solve some problems. And moreover, I will not dive deep into each and every concept that was discussed by Professor Anand, just to save time. And but of course, if you have any doubt, you can stop me and ask. I will try to make you understand in the best way possible. And then after that, after all discussions, we will start solving the problems. Okay, so as discussed by Professor Anand in the lectures, thermodynamics is actually a very vast subject which primarily deals with the conversion and conservation of energy in various forms. Okay, so any kind of work and heat interactions, for example, how a water gets cooled when, or how a hot tea kept in a cup of water gets cooled because of its interaction with the surrounding, which has a lower temperature. And why does the energy transfer occurs from this hot tea to the cold atmosphere, and why not the other way, or can it be done the other way? So these kind of questions, intriguing questions and concepts, are what that is dealt in the subject of thermodynamics. And thermodynamics, and since these energy interactions are something that we deal in day-to-day basis, microscopic level to uh, from the microscopic level to a very large scale interactions, that's why the applicability and the relevance of thermodynamics becomes uh, quite intense. So that's why I think that this course will help us to visualize these kind of interactions, and help us to understand how this energy transfer occurs and why they occur, in the directionality of these energy interactions. So it and help us to understand how we can quantify it, and understand it in the best way possible. So if anybody is taking this course for the first time, I will just give them a quick note that this course, at the very beginning, may seem quite, I would say, quite uninteresting, because it was something that happened to me when I took the course for the first time. But as we see the implication that it has in our day-to-day life, we'll try to appreciate its beauty, and how this course, or how the scientists who designed this course, who contributed to the uh, development of this course, it will help us to appreciate its beauty and its applicability. Okay, so with that little bit of motivation that I could give from my end, let's start the course. Okay, so as in the lectures, if you recall, Professor Anand have thoroughly taken different concepts and definitions that is quite important to start the course. So as I mentioned, this thermodynamics deals with these modes of energy transfer, and these modes of energy transfer interactions are mainly in the form of heat and work. Okay, and moreover, uh, my, my voice may be a bit broken, or I cannot speak that loud today because I'm having a bit cold. So I hope that's fine. I am sorry for that, but I will try to take the course, take this session in the best way possible. But if there is any inconvenience from my end, I apologize for that. Okay, so as I mentioned, there are two modes of energy transfer, that is heat and work. Okay, and as we proceed in the course, we will see how we are quantifying it and which are the thermodynamic laws that deal with these kind of interactions. Okay, and then Professor Anand mentions about the two different approaches of understanding the course. Okay, if you would have taken a fluid mechanics course previously, you would have dealt with the same thing, that again the macroscopic approach and the microscopic approach, and similar to that, for a basic course or for a starter level course, we will try to approach our study from the macroscopic approach, which is the approach that is used in classical thermodynamics and the assumption of continuum. Okay, so the assumption of continuum, it implies that uh, while uh, discussing different laws of thermodynamics and using them to solve real life problems, we will be dealing with different mathematical formulas, okay, or functions, as you can say. And these functions, if you try to approach from the mathematics point of view, the basic requirement of these functions to exist, or functions, or different operators that we work upon these functions, for example differential operators or integrations, the basic requirement is that these functions have to be continuous. At least in the differentiation case, this function has to be continuous, and these functions can only be assumed to be continuous if we approach through this from the approach to this macroscopic approach, like considering that uh, the the variation in the properties or these functions in the microscopic level are ignored, not, I will say not ignored, but smeared out in a way that they tend to behave in a continuous manner. Okay, so I hope that's understandable. We will not dive that deep, but it's just a basic overview that why we are trying to, why this continuum approach is, or understanding this variation of properties as a continuum is important for the for this particular course, or the way that we're trying to approach this course. Okay, and then there's microscopic approach, where the small variation or the in the properties are also considered, or are quite significant, and we approach it through the kinetic theory in the statistical thermodynamics. So this is something that will not deal in this course, so our main focus would be in this macroscopic approach, but still it is important to know both of them. Okay, so coming to so directly diving into the course. So thanks. So while uh, trying to understand the course, we with this course we be time to time we dealing with this system, surrounding, and a boundary. Okay, and a system is anything that upon which our focus is. Okay, for example, when I started this today's discussion, I was discussing about a hot cup of tea. Okay, so if our focus is on analyzing the hot cup of tea, or how their temperature changes in the tea, how the temperature of the tea changes or drops with time, our focus is primarily on the tea that is in the cup. So the tea in the cup would be our system. Okay, and since this tea is being held in a cup, and it is a cup that separates the tea from the surrounding, at least from, say, if it is fully covered, then the entire tea is being what to say uh, enclosed by the cup, so the cup essentially acts as a boundary. Okay, but say if the tea is not covered from the top, then at least from its lateral surface area and the bottom, the cup acts as a boundary, and upper surface, you can say, it's assumed to be open. Okay, and you can assume a imaginary boundary in that area. Okay, but in sorry but in all the cases other than the top of the cup, the cup essentially acts as a very solid real boundary to the T, which is our system. Okay, and surrounding is the atmosphere with which the T interacts for its temperature to go up or go down. So depending upon the scenario of the atmosphere, for example, if the atmosphere is cold, which is generally the case, the temperature of the T will go down by its interaction with the surrounding. Okay, and this concept of, let me just write it down, system plus surrounding encompasses the universe that we see with our very eyes. Okay, so anything that is not that is not the system can be considered to be surrounding. Okay, so these are very so these are very basic terminologies, and I think it's quite easy to understand right now, but it's very important to understand, like, what it's very important, at least for the later part of the course, to be able to differentiate between the system and the surrounding. So it might be the case two we might have focus on, say, two separate cases. For example, say if the cup that I was discussing, for example, let me draw a figure. For example, say now we have a cup which has divisions. Okay, which has divisions. For example, just consider a case where one side of the cup has tea in it, and the other side of the cup has, say, coffee. Okay, it's just a very vague example. Just try to understand. Okay, but for example, say if our focus is on the tea, like we are more concerned with the tea and how we want to preserve the temperature of the tea, then if our entire focus is on preserving the temperature of the tea and how the temperature varies, we want to look upon that. In that case, our uh, sorry our system would be only the tea. Okay, and even though in general it seems like that both the tea and coffee must be that is inside the cup should be our entire system, but it's not the case. For example, if you're just only concerned with the tea, then tea would be the only part that will encompass the system, and rest of the thing, the atmosphere and the coffee as well, will act as a surrounding. Okay, similarly, now if our focus changes to coffee, like for example we want to preserve the temperature of coffee and see how the temperature of the coffee varies with time, then the coffee and the region that it covers will become our system, and the other part, this is the tea and the surrounding, will become the tea and the outer atmosphere will become the surrounding. Okay, so usually we can in fact say it as system 1 and system 2, but if our analysis is only limited to system 1, then system 2 and the atmosphere around it will act as a surrounding. Okay, so that's how we need to be able to differentiate these different systems and surroundings. Okay, so I think this will become quite clear when we are solving some problems. Essentially, when we thoroughly start discussing about the first law of thermodynamics, which is basically written here. So I'm sorry. So Professor Anand just uh, slightly mentions about this in the very first lecture, but I think as we go further in the course, there will be a dedicated section where we will discuss about the first law of thermodynamics. Okay, so in general, if I just want to introduce, first law of thermodynamics is basically the law of conservation of energy. Okay, so here it just states that the net sum of heat interaction would be equal to the net change in the internal energy of the system plus the net work interactions. Okay, so this is the first law of thermodynamics for a thermodynamic process. Okay, now he used this example to show us different types of systems. Okay, we will discuss about it, but let us just try to understand these different systems with the help of this first law of thermodynamics. Okay, so I hope it is clear till now. Yeah. Okay, so for example, let us consider let us just stick with our example that we started the very beginning, a hot cup of tea. Okay, so as I mentioned, say this is the cup. Okay, and this is the handle, and there is tea inside it. Okay, okay. So let us assume that in this case the the tea has higher temperature. So in the atmosphere, let me just write it as T1 and T2, where T1 is greater than T2. Okay, so as you can see, if the cup is just left like this in the open, then the because of the interaction of the T with the atmosphere, the temperature will go down. Okay, so here you can clearly see that there is a certain level of heat interaction. Okay, so sorry, there is net energy transfer between the system and the surroundings. So uh, this delta E, or change in internal energy of the system, is not zero. So there will be a net energy interactions, okay, between the T and the atmosphere. Okay, and there's essentially no work done because we are not doing any kind of there's no there's no kind of work, no work interaction essentially being done on the T, because so in that case the net work done would be zero. But the interesting thing would be, say, the mass transfer. For example, uh, for example, if the vapor above the T, because of it being interacting with the atmosphere, say if it was covered initially, for example, just use another color. Yeah. Say assume that if it was covered initially, uh, the hot tea, the vapors of above the tea would go up and condense in this plate. Okay, and it will again just pour back down on the tea. So the net mass transfer would be zero if it was enclosed. Okay, but if we just remove this cap, that was covering the tea, for example, yeah, then because of these vapors coming out of the boiling tea, there will, even if it's very less, there will be a certain amount of mass transfer. Okay, so there will be a certain amount of mass transfer, so delta M is also not equal to 0. But now let us consider an example where which was essentially used by Professor Anand, that say that the tea, or this, for example, now let us consider tea itself. The tea is now kept in a thermoflask. Okay, so thermoflask is essentially used to preserve the temperature of any kind of liquid that we keep inside it. For example, a hot tea or a cold juice. Okay, so thermoflask basically prevents any kind of heat interaction. Okay, so in that case, delta E would be equal to 0. Okay, because it tries to prevent any kind of heat interaction. Okay. Secondly, again there is no work interaction, so delta W is 0, and again since it is closed, there is no chance of these vapors from the surface of the tea to go outside, so the net mass transfer is also 0. Okay, so this kind of system where the mass transfer, the energy transfer, and the work interaction is 0 is considered to be a isolated system. Okay, so if we look into this first law, the isolated system from the perspective of first law of thermodynamics, then since the net work interaction is 0, so this dW would be equal, delta W will be equal to 0. Then there is no energy heat interaction, so delta E, that is equal to 0. And finally, since both of them are equal to 0, then it implies the net internal energy dE is equal to 0. So the internal energy of an isolated system is equal to constant. Okay, so this is one of the way how we can understand this different types of system. There is isolated system, open system, and a closed system. Okay, so we will look into it. So And just don't worry. So as I mentioned, we will dive deep into it when we thoroughly discuss the first law of thermodynamics. It is just that since Professor Anand introduced it already in the lectures, I am just going through with whatever I was discussed in the lectures. Okay, and okay, and with that comes different terminologies that different standard terminologies that are used to understand this system and surrounding and how we can differentiate it. Okay, so a control volume is a region in space separated from its surrounding by a real or imaginary surface, imaginary boundary. Okay, so yeah, imaginary boundary. I think I forgot to write that. Imaginary boundary. Okay, and if we look into it, why in bracket I have written an open system. Similarly, a system is a specifically identified fixed mass which is separated from its surrounding by a real or imaginary boundary. Okay, so now the thing is, what's the difference between a control volume and a control system? Okay, I should have written a control system actually. So here I wrote down that with alongside control volume I have written a control system. Okay, I'll just underline it. Sorry, an open system, and for a system. Oh, I think yeah, I'm confusing again. I think system only. Okay, an open system. Okay, why? To understand that, let us take this example. For example, now our focus is on just a minute. I'm sorry. Our focus is on analyzing or analyzing a flow of water through a pipe, and understanding, for example, if there is a, say if you are dealing with heat exchangers, okay, and a fluid passes through a pipe, and our concern is how the temperature of this fluid changes as it flows through the pipe. Okay, so in that case, if we try to analyze these kind of systems which has a continuous flow of fluid or flow of mass, then in order to do that, we take the control volume approach. Okay, let us consider it that, for example, this is the pipe that I was discussing about, and the fluid that is passing through this pipe. Okay, so in order to understand these kind of systems, what we can do is we can understand, you can assume a control volume in a particular region of the pipe that engulfs the outer pipe, a certain region of the pipe, this area, and the fluid inside it. Okay, and the flexibility is that this fluid can flow in and out continuously through this particular region, and our concern would only be how the flow of this fluid through this control volume affects the parameters within this control volume. Okay, and that's why this kind of approach, where the mass of the fluid is not or I should say the identity of the mass of the fluid inside the control volume is not fixed. These kind of systems are known as control volumes and are oftenly, and thus these are often used to analyze open systems. And as the term itself tells us, open system would basically imply that there is a net mass interaction or net mass transfer. Okay, so delta M will not be equal to 0. Okay, and in these kind of systems, the mass and the identity of the mass may change with time. Okay, but in the case of a system or a control mass, this this has a fixed mass. This is a fixed mass which is separated from the surrounding, and the identity of the mass remains unchanged. Okay, so this basically tells us about a closed system. Okay, for example, in the case of this thermoflask, where the system was our this hot tea in the thermoflask, so you can see that even if there is, say for example, evaporation and condensation within the thermoflask, but the identity of the mass within the control system remains the same. Okay, so that's why it essentially represents an closed system. Okay, so a control volume approach is often used to understand to analyze its open systems, and this control system or control mass approach is used to analyze these closed systems. Okay, where the identity and the amount of mass remains constant. Okay, but in the case of control volume, here in this case, if the flow rate, say m dot is, or delta m dot is equal to 0, it is the mass flow rate does not change with time, then we can say that the quantity of mass remains same, but the identity changes because there is a continuous flow of fluid through across the control volume. But say if the mass flow rate is not constant, then we can say that along with the identity, the mass of the fluid inside the control volume also changes with time. Okay. So as I already mentioned, in the case of open system or control volume approach, the mass, there is mass, heat and heat transfer along with work interactions. Okay, so delta M and delta E, delta W are not equal to 0. Okay, but in the case of a closed system and a control mass, there can only be heat interactions. That's why delta M and delta M is equal to 0 and other two may not be equal to 0. Okay, but in the case of isolated systems, that is the case of thermoflask, there is no heat or work interaction or no mass transfer either, so delta M, delta E and delta W all are equal to 0. Okay, so I hope this was clear till now. If there is any doubt, you can ask. Okay. Okay, it's fine. Okay. So now let us again discuss a bit more on other specific terminologies related to this course. Okay, so let's start with some thermodynamic properties. Okay, so a thermodynamic property, or just a property from the perspective of thermodynamics, is a measurable macroscopic characteristic of the system. Okay, for example, temperature. In the case of this hot tea, temperature would be the property that we are concerned with. Okay, so temperature is a property of the system. Along with it, it can have, we can quantify it using, say, different examples. For example, if you close the upper surface of the cup and say try to understand how these evaporating water molecules from the tea exerts pressure on the upper lid, or just want to see how the vapor pressure from the tea is building up because of the evaporation, builds up with time, you want to quantify that, then pressure would become another thermodynamic property. Okay, in this case. Okay, and there are again different I would say properties that are being that are again defined from the for example, again the internal energy that will come in, that we understand when we look into the first law of thermodynamics, the internal energy, and again enthalpy. Okay, so an enthalpy is again quite relevant when we are dealing with systems having continuous flow of fluid. Okay, so in the case of systems having continuous flow, enthalpy becomes the more relevant thermodynamic property compared to the internal energy. Okay, so we'll look into it when we dive deep. So these are some different properties that I would say quantifies a thermodynamic system. Okay, or characterizes a thermodynamic system. Like, say if you are looking into hot property, what are the things that you are concerned with? What is temperature? So temperature is a primary thermodynamic property. Okay, so, and say for example, if you are trying to measure the pressure inside your cycle tube, okay, for example, then pressure in that case would be your thermodynamic property. Okay, or for example, say if it gets deflated with time, then say you are concerned with what is the volume of air inside the tire or tube, cycle tube, and how it changes. So in that case, the volume of air in the cycle tube becomes your thermodynamic property. Okay, I hope it's understandable. I understand it's very basic, but it's important to know. Okay, and there are some standard terms that are used and which will be continuously using in the as we proceed further in the course. So that's why it's quite I would say good if we are just quite well versed with these terminologies. Okay, and again, these thermodynamic properties can be broadly classified into two types, that is in extensive properties and intensive properties. Okay, I will come into the specific properties, but in general these are broadly classified into extensive properties and intensive properties. Okay, so there's a very good way to classify. So if you are confused with something, then it's a very good way to classify these thermodynamic properties. For example, you can see that in the word extensive there is a word extent, okay, or extend. So these extensive properties basically depend on the extent of the mass of this particular property. Okay, extent of mass. So extensive properties must depend on the extent of mass of that particular property. So in that case, these extensive properties would include mass, volume, energy, and enthalpy. Okay, these are just some examples. For example, in the case of say let me say again, let us take an example of cycle tube. Okay, for example, initially the volume that it encompasses when it's deflated, say it is around, say I'm just giving a very vague value. Okay, just don't take it seriously, just a vague value. Say it is having a volume of let's say 500 centimeter cube. Okay, just a very vague example. Okay, then after some time, say when we inflate it using a cycle pump, okay, the volume now becomes say 1000 centimeter cube. Okay, so you can clearly see that, and see that this volume is now depending on the extent of your cycle tube. When it was deflated, it 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 covered it covered a comparatively lesser area, but after it gets inflated, now it covers more area or has a greater volume. Okay, so this depends on the extent of your system. But now take another case. Okay, that is the intensive properties which are independent of the quantity of mass. Okay, so, or in other way you can say that since V2 is greater than V1, you will definitely see that this, if the density of air remains constant, because it will remain constant in that particular flow regime, then you will see that the mass of the air in the case of, in this case, say M2 and M1, so M2 is greater than M1. Okay, so it depends, in one way or another, it depends on the extent of the system. Okay, this volume. Okay, now in intensive properties, these are independent of the quantity of mass or the extent of the mass. For example, say temperature. Okay, for example, just a second. Yeah. Again, let us take the example of the hot cup of tea. Okay, I think I should stick with that so that all these properties can be understood well. It is hot cup of tea. Okay, and say there is a certain volume of tea inside the cup. Then say considering that there are no rapid fluctuations in the temperature, and considering these small minute changes in the temperature because of the temperature gradient and the proximity of the tea near the tea surface, we can essentially consider that the temperature of this tea remains uniform. Okay, for example, now if you say transfer a certain amount of tea outside a smaller cup, instantaneously, for example, like just at that time, then you will see that, say this is T1 and here this T2, that right after the moment you transfer this to a smaller cup, and obviously the inside this smaller cup has a lesser volume and a lesser mass, but you will see that T1 would be equal to T2, like independent of the mass of the T inside the cup. Okay, it won't depend on the mass or the volume that is covered by the T. Okay. Similarly, the density, this density of the T inside the cup, say if it's not not modified by the T leaves in the water, then it will essentially be 1000 kg per meter cube. Okay, it's basically density of water. But even after you transfer it to a smaller cup or even a very huge cup, then the density of the T would essentially remain constant. Okay, so these are the properties that are independent of the mass. Okay, but for example, in this case itself, when you have transferred the T from this larger cup to a smaller cup, say this has now volume V2 and a volume V1, then you'll essentially see that this V2 is lesser than V1. Okay, so you'll see that how when some properties are dependent on the mass of the system and some are independent of it. Okay, so this is the way that we can differentiate these thermodynamic properties. Okay, and this intensive properties again has one other classification, or I would say one other special case, that is the specific properties. Okay, so I'm not highlighting it because the pencil is charging, so I think whatever there's on the screen, I can just read it out. So if there's any doubt, you can ask, but I will let the pencil charge for some time. Okay, so there are specific properties. Okay, the specific properties are basically the extensive properties divided by its mass. For example, as I mentioned, that this enthalpy internal energy capital E and enthalpy capital H are the extensive properties. So as the mass increases, this enthalpy and internal energy would increase. Okay, it's dependent on the mass. But for example, if you're concerned with if we divide these properties by the mass of the system, then they represent an intensive property because they are becoming independent of mass. Okay, and these kind of properties are not specific properties. For in this case, for example, small h would be capital H by m, where capital H is your enthalpy or the total enthalpy, and small h represents the specific enthalpy, total enthalpy divided by its mass. Similarly, the small v represents your specific volume, that is the total volume divided by its mass, and similarly small e represents the specific internal energy, that is the total internal energy divided by its mass. Okay, so I hope it is clear. So now we can proceed. Sorry if my voice is down or broken, and having a bit difficulty with the cold. Yes? Oh, yes? Is there any doubt? Someone unmuted it seems. Okay, it's fine. Yeah. Now comes another terminology, that is the state of the system. Okay. So a state of the system is defined as the set of all properties that are required to completely define a system. Okay. Just 1 second. Just 1 second. Okay, just 1 second. Can you ask questions by unmuting? Yeah, please. Yes, you can ask. Yeah. What is this?
Hello, sir.
Yeah, hello.
Yeah, thank you for allowing me to ask the question.
Yeah, sure.
Sir, in one of the lecture, Professor Anand said that if we take down one system and having two parts, say one partition in between, one part is totally no pressure, absolutely no pressure in that, and in one part there is a pressurized air. And if we puncture the membrane, then or say remove the partition suddenly,
Hmm.
the gas will expand, right? And the work done by the gas is zero.
Hmm.
Is that correct?
Yes.
Yeah. So, but if we apply, imagine that the boundary of the system is a adiabatic boundary. There is no heat transfer is taking place across it, right?
Hmm.
So, after a certain expansion, in that process, if we apply the first law of thermodynamics, delta Q is equal to delta U plus delta W.
Hmm.
So, delta Q is zero.
Hmm.
So, after expansion, there will be somewhat drop in temperature. Am I
Okay.
right, sir?
Okay. Yes.
If there is a drop in temperature, there will be non-zero value of change in internal energy.
Yes.
So, there has to be a non-zero value of work done also.
Okay. So you are saying that free expansion, in the case of free
Yes.
expansion, there has to be a non-zero work done, right?
Yes, sir.
In that case.
Yes, sir.
Okay. So
So if we take down the boundary as insulated, if we insulate that system, entire system, and if we allow to have the free expansion,
hmm.
and to that free expansion, if we apply the first law of thermodynamics, where delta Q is zero, as system is insulated, and due to the expansion, there is a drop in temperature, so there is change in internal energy,
Okay.
and due to the expansion, there is a change in pressure also. So there has to be somewhat work done. Now it is true that there is no restrictive force restriction for the expansion. But if we go by the theoretical way, by following the first law of thermodynamics, delta Q is equal to delta U plus delta W. So delta Q is zero and delta U has a non-zero value. So delta W must have some non-zero value.
Okay.
That's perfect, sir.
Yeah, I'm just trying to understand. I understand the question is nice. So I'm just trying to see whether I can understand. Whether I can look into it in this session. Otherwise, I think if you join the next session, I can try to answer that. But let us just try to look into it. What you are trying to mention
Yes, sir.
is equal to zero, and you are saying because of the free expansion, because of this gas expanding, there has to be a change in internal energy and work done. Right.
Yes, sir. If you write down the statement for the first law of thermodynamics, yes, sir.
Yes.
Now in this case, delta Q is zero,
Yes.
right? Now as the gas is expanding, so there is drop in temperature.
Okay.
So if there is a drop in temperature, the internal energy will change. The delta E will change.
Hmm.
So if there is a non-zero value of delta E, there has to be non-zero value of delta W also.
Okay. Uh,
So following this equation, delta W is not zero. Whereas we have seen that in case of free expansion, work done is zero.
yes. Yes. Uh,
If I'm wrong,
no, no,
please
no, no,
let
no,
me
no,
know.
no, no. It's
So
absolutely fine. It's a nice way to look into it. I'm just trying to see whether I can answer it right away or not. So, uh, yeah, the thing is that change in the internal energy has to be balanced out with some work. Okay, but I'm just concerned that is this work entirely, as you mentioned, entirely because of free expansion, or there is some other kind of work that has to be generated from the system. That's the case. Okay, so you can say, and what about the system boundaries? Is it rigid,
system boundary is rigid and insulated.
rigid and insulated, right? So yeah. So the thing is, uh, PdV, this in the case of this work, PdV work would be equal to zero, right? PdV work will be equal to zero, but other kind of works that Professor Anand might have mentioned might be there. Okay, so work done is not only always PdV work. There can be other kind of works as well. Okay, so there PdV work might be zero, but the other kind of work interactions may not be 0. Okay.
Yes, sir. I agree. But sir, as of now, what are the system that we are discussing? That there is only like expansion type of work. There is PDV type of work. Since no electrical work, no shaft work, so other works are almost like not existing over there. Like as that I can see. If there any other possible work done that is happening over there, please let me know. Like
Yes, that's the thing. And expansion. Okay. The thing is, uh, okay. So the thing is, would you be willing to join the next session as well?
yes, sir, for sure, sir.
Yeah, for sure, right. So, would you give me just time till the next session if I just could look into it? It's a very good question actually. I'm just maybe just uh, how to say I'm
uh,
not I'm not able
yes.
to look into it right now. So,
Not an issue, sir. Just I came across that, sir. And actually, sir, there is one more question. Definitely, I will join the next session also, sir. Not an issue. There is another question, sir.
sure, sure.
So in the lecture, sir mentioned that if the apple is falling from the tree and coming down,
Yeah.
so the work done is 0. So my question was that like whether the sir mentioned about the work done by the gravitational force on the apple or work done by the apple. So I didn't understand like which work done he mentioned.
Okay. So, I think if you don't mind, I think we are right now. It's of course the work done on the apple by the air resistance in that case. Okay. So in the case he
Okay.
mentions that if there's no air resistance, there's no work done. But if there's air resistance, there has to be certain amount of work done done by the apple against the air resistance. Okay, so there is work done by the apple against the air resistance. So it's work done by the apple.
Okay, okay, sir. Fine, sir. Fine, sir.
Yeah,
Thank you, sir.
yeah. So
Sir,
yeah, yeah, yes.
yeah. Shall I ask you one more question? I don't know, sir. This is my first time to attend such a session. So whether we are allowed to ask the question or not, I'm not
No, no,
aware.
no. Yeah, the thing is, yeah, you're of course allowed to ask the question, but the thing is, if I'm not wrong, you are currently asking questions regarding the week two topics. If
Yes,
I'm not wrong, yeah, yeah, yeah,
week two topic,
yeah.
right, sir?
But the thing is, this session is for week one
Okay,
session.
okay,
Oh,
okay,
but
sir.
you're
Fine.
no, no. That's what I'm saying. You're open to ask question now, but the thing is, since this session is only like quite specific to week 1 topics, so that's why I will not be discussing what the week 2 part is, the work done part that was discussed by Professor Anand in the lectures. But you're open to
Fine,
ask
sir.
questions right now. So what's the question? Just can I see?
So I have the question, but I will ask it in the next session whenever the questions related to the week two are going on.
Yeah, yeah. Okay, then that's fine. But I hope you understand it, right?
Yes, sir. Yes, sir.
Yeah,
Thank you, sir.
sure.
Thank you.
So,
Yeah.
so I see Jay also having a doubt. So, Jay, would you is it related to week 2 session?
No, sir, it's only related to Week-1.
Yeah, yeah, sure. Can you please ask?
Sir, the concept of work done or given by C, the most main part of it somehow makes me confused about the idea of work done. Like there is displacement, there is force applied, but when the piston goes up, the work is taken as zero in conditions.
Can you please? I think I heard some part of the question, but there's a bit. It's a bit unclear the voice. So could you please maybe adjust your mic and just say it again, Jay? Am I audible, Jay? Yeah, yeah, sure. You can type. So meanwhile, I think we can proceed with the discussion. You can type your question, and then after I see the question again, I will maybe try to answer it. Okay? Yeah.
Excuse me, sir.
Yeah, yeah,
Yeah. Deepak Biradar here.
yeah, yeah.
Once again.
Sure, sure. I yes.
Sir, I don't remember which was that lecture. Was the lecture belonging to first week or second week?
Okay.
But in one of the lectures, sir mentioned that in case if summation of F is equal to 0,
Okay.
summation of net force acting on the system is 0,
Okay.
doesn't mean that work done is 0. So I didn't understand like how is this possible? Like even one net force acting onto it is 0, and still there is non-zero value of work done. And in real life situation, I never came across any such example. So if you have any such example where summation of F bar, that is summation of all the forces acting onto a body is 0, and still there is a non-zero value of work done.
Uh,
I don't remember this from
no, yeah.
lecture
This is
one or two.
this is from week 2. Since you are again discussing
Okay,
about
okay.
work done, but the thing is, uh, yeah, there can be such scenarios, right? For example, say if you just do the force balance on a system,
Okay.
so
Hmm.
then like say if you just resolve the force along the direction and magnitude, it may turn out to be 0, but the pdv work in that case may not be equal to 0, right? Or
Okay.
so I think that's the
Hmm.
case. Let me just look into it. Okay, just wait 1 second. Maybe if I just look into it, I will be able to answer that. Just wait 1 minute.
Yes, sir.
Yeah, sure. And meanwhile, Jay, you can type your question. So yeah, I think I encountered this case. Uh, what force? This. Just 1 second. Okay. Summation of f equal to 0. It doesn't make work done equal to 0. Okay, so I think I need to look into it, maybe to make you understand it in a better way. Okay, I will just look into it and maybe discuss in the next session. Is that okay?
Yes, sir.
Yeah,
Fine, sir.
these
Thank you,
two
sir.
files, this uh, heat interaction, work interaction is in free expansion, and this question, right? Because
Yes, sir.
yeah, I also marked it down in my end as well. I was concerned, I having doubt in this part as for my end as well. That's why I marked it down as question mark in the notes.
Okay,
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 so
sir.
I'll just look into some examples. Maybe we will be able to discuss it in the next session. Okay.
Okay, sir. Okay. Thank you, sir.
Okay. Okay. Thank you. uh, okay then. Meanwhile, Jay, you can write the question, and then I think we can continue with this session. Yeah. So yeah, as I was mentioning, this state is a set of all properties that are required to completely define a system. Okay. And for example, I can say, for example, if we consider two, in the case of thermodynamic system, the two properties that are usually taken, the properties that are of primary concern are primarily pressure, volume, and temperature. Okay, and in any point of time, if you know either two of them, that is either pressure or volume or temperature, or pressure or temperature, you can tell the state of the system. Okay. State of the system would basically imply, for example, if you are considering water, then there are three primary states, right? Vapor, liquid, solid, it is in the form of ice, liquid, that is in the form of water, and vapor in the form of gaseous is in the form of water vapor. Okay. So in any point of time, say if you know the pressure and temperature, then you can know whether your water is in solid state, in liquid state, or gaseous state. Okay, so that's what we mean by knowing the set of properties that are required to define a system. Okay, and in the case of thermodynamics, in general, we need only two properties. In general, we need two properties to completely define a system. Okay, for this requirement, the number of systems to define a state comes from a Gibbs phase law that is given by F plus P is equal to C plus 2. Okay, where F is the degrees of freedom or the number of independent properties required to define a system. P is the number of phases in the system. C is the number of components, and 2 is just a constant value. Okay, for example, in the case of water, okay, say water at 50 degrees Celsius, we know that it will be in liquid state, right? Because it is greater than 0 degrees Celsius and lower than 100 degrees Celsius, so it is in liquid state. In that case, number of phases is equal to 1, right? Because it is in a homogeneous phase, so and it is homogeneous throughout. Then number of phases in the system is equal to 1. Number of components is also equal to 1, because in this case we are only considering about water, right? Then if we substitute the value of P equal to 1 and C equal to 1, you will see that F would be equal to F plus 1 is equal to 1 plus 2. Then F turns out to be equal to 2. So in the case where the temperature of water is 50 degrees Celsius, and say the vapor pressure in the water is lower than the vapor pressure of evaporation or boiling pressure, so not evaporation, I would say that vapor pressure of boiling pressure, okay, lower than the boiling pressure, lower than the pressure corresponding to the boiling. In that case, your degree of freedom required to define the state of system in that particular case would be equal to 2. But now consider a case where the water is about to boil or about to melt. Okay, it is basically in the case when the water starts to melt, it is at 0 degrees Celsius, and water starts to boil at 100 degrees Celsius. Okay, at that point of time, the phase remains uniform. Okay, so number of phases is equal to 1, but number of components is equal to 1, but the phase is equal to 2. Why? Because when the water starts to melt or starts to boil, there are two phases are in equilibrium: the solid as well as the liquid in the case of melting, and liquid and the gas in the case of boiling. Okay, so number of phases become equal to 2. So in that case, we will have F plus 2 is equal to 1 plus 2. In that case, we have F is equal to 1. So it basically tells us that in the case when the water is when the water is at the boiling state and the melting state, then knowing either the pressure or the volume or temperature of the water, we can know about the state. Okay, these are special cases or special points in the in say the pressure, volume, or the pressure, temperature, or temperature, volume plots, where we can distinctly define the state of system using only one property. Okay, but in other cases where the water is either completely solid, liquid, or gaseous, and phase change does not occur in those cases, then the degrees of freedom required to completely define a system is equal to 2. Okay. So I hope this was clear. Then let us look into a thermodynamic part. These are just the definition that was discussed in the class. I'm just going through it just so that we are just well versed to discuss the course in a better way. Okay. So path is the locus of all the intermediate states which the system passes through to change from one state to another. Okay. So basically, if you look into this diagram, say the system changes from state 1 to state 2. Okay. In state 1, say again, take the example of water only. Say water is changing from phase 1 to phase 2, and state 1 to state 2, and at the state 1 we know both the pressure and temperature, and state 2 we know both the pressure and temperature. So the locus of all these intermediate states, say from say 1 to A, B, C, D, all the way to say 2. So if we just draw a locus of all these intermediate states that the system has passed through to reach from 1 to 2, this locus of these intermediate states will be represented, will be called the path of the system. Okay. And if the final and say example, for example, again, if the system is changing from say point 2 to point 1, then if the final point and the initial point of the system, or the final, I would say that in the thermodynamic way, the final state and initial state of the system is same, then we can say that the system has undergone a thermodynamic cycle. Okay. That is, the initial and the final state of the system is invariant. In that case, the system is told to undergone is said to undergo a thermodynamic cycle. Okay. And there was again a concept of a reversible and irreversible process. Okay. Yeah. So I would say right now we can just say reversible process is a process where the system goes from one state to other state, say in a very slow manner. Okay, in a very slow manner, so that each and every intermediate state are at equilibrium. Okay. So say reaching from point 1 to point 2, the system has to go through an infinite number of equilibrium states. Okay. And all these states need to be at equilibrium. Okay. And see, since a rapid change from 1 to 2 might cause irreversibilities, then that's why when a process is done in such a slow manner that each and every state that the system passes is in near equilibrium, these kind of processes are known as reversible processes. Okay. That's why again these are also termed quasi-static processes, because quasi-static will basically mean that almost static, not static but almost static. Okay. And why is it done? So that the reversibility in the system can be minimized as much as possible. Okay. And it is these reversible processes that can be represented as solid lines in this PV plots, TV plots, and PV, TV, and pressure temperature plots. Okay, so this can be represented as solid lines in this kind of diagrams. Okay, we'll dive deep into it when we discuss about different this pressure volume diagrams and different examples. You'll be able to clearly distinguish why there's a requirement of two separate representations are needed to quantify these processes, reversible and irreversible processes. Okay. So yeah, I hope this is clear. Then let us okay. So now we'll briefly discuss about exact and inexact differentials. Okay, and I think this was thoroughly discussed in the lectures, but still, I think it's needed for me to just briefly go through them so that the distinction becomes quite clear. Okay. So this the requirement of understanding exact and inexact differentials come from the requirement to understand or distinguish between state functions and path functions. Okay. So it basically means that properties that are dependent on the state and properties that are dependent on the path followed by the system. Okay. So any properties that are only dependent on the state are known as on the state of the system. For example, if I go back here in this diagram, I hope this is visible now. Let me zoom out a bit, yeah. Then say, for example, the properties, say in point 1 and point 2, if they are dependent only on their location at the PV plots at the states P1 and P2, at states 1 and 2, then these kind of properties are known as state function, because they are only dependent on the states. Okay. But if there are certain properties that are also dependent on the path followed by the system, like in which manner the change in the state was attained. Okay, for example, that as Deepak might have mentioned about adiabatic process. So one can go from state 1 to state 2 through an adiabatic part, or a isothermal part, or isobaric part. Basically, isothermal will mean a constant temperature. Basically, if the state change occurs in a constant temperature manner, then we can say that this is an isothermal part. If the heat transfer is 0, then adiabatic, and if the pressure remains constant while changing from state 1 to state 2, then it is isobaric. And in that case, if our property that we are measuring is depending on how this change was obtained from state 1 to state 2, these kind of properties or functions are known as path functions. Okay, and basically the state functions represent exact differentials, and this path function represent inexact differentials. Okay, and there are different ways to represent them in the perspective of thermodynamics. For example, in the case of, say, first law, this is written here, you will see that there is distinctly a cut on this differential operator on the heat and the work interactions, and there is no cut on the differential operator on the internal energy. So it basically states that these heat and work interactions are inexact differentials or path functions, and your internal energy here in this case is a complete differential or exact differential, and is indeed a state function. It is independent of the path followed to have the change in the state of the system. Okay. So from now onwards, when we are trying to represent any kind of small change in the exact differentials or state properties, for example, internal energy, pressure and volume, we will represent them using this only simple differential operator dP and dV. Okay, but in the case of path functions such as work and heat interactions, we will use this delta operator or this d cut. Okay, this is just notation, but it's important to know the difference. Okay, yeah, and then there was an extensive discussion on how uh, we can Professor Anand just went to some mathematics to look into this, to differentiate these different kind of uh, functions. Okay, state functions and path functions. Okay, so let us look into it, how to distinguish them. Okay, for example, say our property, this say this, we are considering a function z, okay, which is a function of x and y. Okay? Then a complete differential of z, this dz, can be represented as dou z by dou x times dx, where dou z by dou x means that the partial differentiation of z with respect to x, okay, it is plus dou z by dou y times dy. Okay, so this is a very standard mathematical definition to represent a complete differential. Okay. And if your this z is a state function or a complete differential or exact differential, then we'll have that dou by dou y of dou z by dou x would be equal to dou by dou x of dou z by dou y. Okay. So this is what it is shown here. So for example, if this is the case, then let us represent dou z by dou x as m, dou z by dou y as n, then dz is represented as m dx plus n dy. Simple mathematical steps. I don't think it's quite complicated. Then dou m by dou y is dou square z by dou y dou y times dou x. Dou n by dou x is equal to dou square z divided by dou x by dou y. Okay. Then if dou m by dou y is equal to dou n by dou x, then it represents an exact differential. So this is the way or a mathematical way then that you can classify the path independence of different properties. Okay. So let us try to solve some examples. I think this was taken in the class, but let us just go through it once. For example, let us consider this case. Discuss the path independence of these different cases. Okay. For example, dz is given by integration from 1 to 3 of p dv. Okay. We need to see whether this z represents a exact or inexact differential. Okay. So to do that, you will see that this z now is dependent as a function of both p and v. Okay, in general. Then dz would be dou z by dou p times dp plus dou z by dv times dv. Now if we try to compare it with this integral, then we will have that dou z by dou p is equal to 0 because there is no dp term in the equation, but it has a dv term, right? Then it implies that dou z by dou v is equal to p, comparing to this equation. Okay. Then it implies that dou by dou p of dou z by dou v is equal to dou by dou p of p, that is equal to 1. But here dou by dou v of dou z by dou p is equal to 0. Then it implies that since these two are not equal, then this is not path independent, or it is an inexact differential. Okay. Similarly, if we consider this case, dz is equal to integral from 1 to 3 v dp, then z is equal to is function of p and v. Similarly, we are going to do the same steps. Dou z by dou p, dz is equal to dou z by dou p times dp plus dou z by dou v times dv. Then comparing to this equation, dou z by dou p is equal to v and dou z by dou v is equal to 0. From here itself you can say it is equal to 0, and this is a function of v. Then dou by dou v or dou z by dou p is not equal to dou by dou p or dou z by dou v. Then this is an path dependent process. Okay. But now comes a case where we write dz as integral from 1 to 3 p dv plus v dp. Okay. Then in this case you can see that z is again a function of p and v. Okay. Then dz is dou z by dou p dp plus dou z by dou v dv. Then comparing to this equation, you will get that coefficient of dv is p, so dou z by dou v is p. Coefficient of dp is v, so dou z by dou p is v. Then if you compare this, then take the differential of this with respect to v, then dou by dou v or dou z by dou p is equal to 1. Similarly, dou by dou p or dou z by dou v is equal to 1. Since these two are equal, so this represents a path independent process or an exact differential. Okay. Yeah. So now let us take an example. I don't know whether this is taken in the class or in the assignment. So let us take this example. So you need to tell me, okay? Yeah. For example, if a change in properties of phi, this delta phi is f of t dt plus rt v times dv. So okay. So question is phi a property of the system? Okay. You need to look into this using this kind of calculations. Find whether phi is a property of the system, and if not, what are the changes that needed to be made in the definition to make this an exact differential. Okay. So I will give you say 3 minutes to look into it. It's quite simple. Use the same steps as discussed here, and then say whether this phi is an exact differential or an inexact differential. Okay. It's 7:19, so I have 7:22. I hope I can get some answers. So did no one get the answer? Deepak, are you in the class? So,
Yes, sir, I'm in the class, but couldn't solve it.
okay, sure. So, okay, so let's look into it. I think it's quite simple. Okay, so fine. Okay, let us consider. Let us start with the same differential understanding. Okay, so phi is a function of temperature and volume, because you can see the only independent properties that we have in this case are temperature and volume. Okay, so we can essentially write phi as a function of T and V. Okay, then d phi is dou phi by dou t dt plus dou phi by dou v dv. Okay, I hope it is clear till now. Then uh, uh, if we compare the coefficients, this ft and this, then you can get that dou phi by dou t is function of temperature T, and dou phi by dou v is RT by V. Okay, uh, then you can see that this dou phi by dou t is only a function of temperature here. Okay, so if we have dou by dou v of some function of temperature, see dou by dou v is partial differentiation of a function with respect to v. So since this is only a function of temperature, then dou by dou v of f of t is 0. Similarly, dou by dou t of RT by V is equal to R by V. Since these two are not equal, we can essentially say that phi is not a property. Okay, that's the first part of the question. The second is the second is that what are the changes that we need to make on phi to have phi as a property of the system. So you can see that here dou phi by dou t is RT by V. Okay, sorry, dou by dou t of RT by V is R by V. So here you can clearly see that in this case, if there was a scenario where this argument has no temperature in it, no temperature dependence, then dou by dou t of R by V is also equal to 0. So if we just change the coefficient from RT by V to R by V, then this becomes a property, right? We can just look into it. So if we write d phi, delta phi as f of t dt plus R by V dv, then we have dou by dou v of f of t is equal to dou by dou t of R by V. This is equal to 0 and this also equal to 0. Then it will imply that phi is a property of the system. Okay, so this is a required modification that we needed to make. Okay, so you can just look into the calculation. So if there's any confusion, you can ask. Then we can just. So is it clear?
Sir,
Yes, please.
we have taken f of t as one function and we have differentiated it with respect to v.
Yes.
So, like f of t, it means that function is only of t and not of v.
Yes, only of t and not of v. Yes.
But how can we say like that? Like it may be the function of v also.
No, but it represents here, right? F of t only, right?
F of t only.
Yes.
So if there was the function of v, then f of t comma v should have been there, right?
Yes. Yes. Exactly.
Okay, 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 fine. Thank you, sir.
Thank you. Then thank you. Then I think this is clear. Okay. So Deepak, can I just go back to your question? This one, I just while you were scrolling, I was just looking into the internet. So yeah, and the better, or I would say the complete understanding of this would require, I would say, a thorough what to say, thorough a deep dive to the concept thermodynamics, which would include some advanced concepts. Okay, with enthalpy, entropy, these things we need to understand. But Right now, can I say it using a very simple conceptual understanding? Is that fine?
Yes, sir.
Yeah. So it's actually a very good, intriguing question. Like usually don't expect. Like I myself didn't think right away, but the thing is, you are mentioning that this is an insulated system, right?
Right, sir.
Right, and you are saying that there is a free expansion and the gas would expand and do some work.
Yes, sir.
Yeah, but the thing is that since no, it won't do any it won't do any work. But how there is a change in internal energy, right? That was the question. If it is free expansion, right? Let me just write the terminologies here as well. Free
Yes.
expansion. Yeah. Okay. So the thing is that approaching this problem from the concept of free expansion. Let's start with that. You are saying delta Q is equal to 0, and free expansion it will imply delta W is also equal to 0. Okay. So in this
Delta
case,
W won't be equal to 0.
no. I'm just saying, like, just consider
Okay.
that we are doing free expansion and delta W is equal to 0.
Okay.
Okay. In that case, you are it should essentially imply that delta E is equal to 0 and there should be no change in the internal energy because it depends only on the temperature. So there should be no temperature change. You are saying that since the gas will expand, there should be a temperature change, which is obvious. Okay, right,
Right.
right. But the thing is that in this kind of scenario, if the system is not exchanging any kind of heat uh, and not doing any kind of work, it will directly imply that delta E is equal to 0. Why? Because in the case of, say, ideal gases, the internal energy E is only a function of temperature. Okay,
That's correct.
yeah, T2 and T1. Yeah. And
That's
since,
correct.
yeah, and since this is not changing, because both of these terms are 0, then the internal energy of this for an ideal gas won't change.
But it will leads to the like it means that the expansion is taking place by isothermal way. So it will be the isothermal expansion.
Uh,
If temperature is not changing,
yes.
it means it is the isothermal expansion.
Yeah, you can say in this
Am I right?
for ideal gases. Yeah, for ideal gases, yes.
But even for the isothermal expansion, there is somewhat work done.
That,
So we cannot say that isothermal expansion is there. Volume is changing from V1 to V2. So in that case, also work done is not zero.
no. Work done is 0 because of isothermal expansion. Right? For no, for this free expansion, right? Free expansion, because we are considering free expansion as your question, right?
That's fine, sir. I understood that the free expansion, we already assumed that delta W is zero.
Yes.
And it is due to the reason that like internal energy is not changing.
Yes.
It is due to the reason that temperature is not changing.
Yes.
But if the temperature is not changing, it will be an isothermal process.
Okay. Yeah.
Am I right, sir?
Yes.
So, but even for the isothermal process, if it is changing state from 1 to 2, there will be somewhat work done.
No, but it is not changing the state, right? Since it is only dependent on temperature. For I'm just saying for ideal gases. For real gases, there will be some change in temperature. That's what I was coming into. Okay. If it is clear now, this kind of expansion is known as this Joule expansion.
Yeah.
Yeah, so
Right, sir.
yeah, I have not reached to that part, and maybe I will take some time as well to understand it in a better way and make like everyone understand in a better way possible. But to understand that, I think all the students here who are new to the course will take some time to understand that, right? They need to be well versed with the concept of enthalpy change, entropy, and how these inversion curves occur in the case of real gases, right? Yeah, but right now, since I cannot do that, I will just say that for ideal gases, since there is no temperature change, this delta E will also be equal to 0 and there will be no work done. But for the real gases, there would be a temperature change, and that can be only understood when we discuss the topic of Joule expansion, right? Would that be okay if I say?
All right, sir. All right, fine, sir.
Yeah.
But just looking at the general case,
Yeah.
general case is that when the gas is expanding,
Hmm.
the volume is increasing and pressure is dropping down.
Yes,
There
exactly.
has to be change in temperature.
Yes,
The temperature has to drop down.
yeah, exactly. That's what happens in the real case. Right? I'm just saying this for ideal gas, only for
Okay.
ideal gases.
Even
Not
for the ideal gases, it will happen, sir.
But for the scenario that you are mentioning, that it is insulated as well as there is free expansion, then the temperature won't change. That's the conclusion. Yeah, it cannot change. It won't change. If the first law of thermodynamics is satisfied, temperature won't change. That's the thing.
All right.
Yeah, that's the way. Like if you just look into this definition itself, the temperature won't change because internal energy is remaining constant, right? So if this is constant, then T1 and T2 has to remain constant, right? Cv is essentially a constant, then T1 and T2 has to remain constant to keep this as a constant to preserve the first law of thermodynamics, right? But the thing is, when if at all we come to Joule expansion, understand Joule expansion and Joule expansion coefficients for different gases, real gases, then we will understand why this how this temperature change is compensated in the system, even in the case of free expansion.
Did you mention about the Joule Thomson coefficient or
Yeah,
Joule coefficient?
yeah. No, Joule expansion. I'm just saying Joule expansion. Yeah.
There's some coefficient you just mentioned.
Yeah. When we look into it, we will discuss that, right?
Okay,
Yeah.
fine. But sir, I still think that like this general gas, like even for the ideal gas, the temperature has to drop down. If we take down the general gas equation, that is PV by T is equal to constant. If we apply it for P1 V1 by T1 is equal to P2 V2 by T2. So even in that case,
what did you mention? Can you just tell again?
That is P1 V1 by T1 is equal to P2 V2 by T2.
Let me just write it. P1 V1 by T1 is equal to
P2 V2 by T2.
Okay.
So that's what the general gas equation. The PV by PV is equal to nRT. So even in this, even if you look at simple examples of pressure volume, the pressure like volume is increasing, pressure is dropping down, there is somewhat expansion. So there is somewhat expansion means there is somewhat loss of pressure energy also. So where does that pressure energy goes then? So in this, if you follow this equation, P1 V1 by T1 is equal to P2 V2 by T2, and if you are saying T1 is equal to T1 is equal to T2, it will become P1 V1 is equal to P2 V2.
Yes.
So it will appear like it is isothermal expansion. It appears like isothermal expansion. Am I right, sir?
Okay.
Okay. Now, if you try to draw that process on PV diagram,
it will give rectangular hyperbola, right?
And if you look at the area under that curvature, it's a non-zero area.
Yeah.
So it means somewhat work done.
Yeah, but the thing is, we need to also impose the adiabatic condition as well.
So right. The role of adiabatic is that it is simply delta Q is equal to 0. So that we already taken.
Okay. Yeah, that's what I'm saying. Like, when we are considering this PV diagram in the case of an isothermal case, which will give a rectangular hyperbola in this particular case, so we are only imposing the isothermal condition. No, we are not imposing the adiabatic case in this one, right? So.
All right, sir. So I think I also need to study a little bit.
No. I understand. See, this is something that I just read, and since I had that idea in my head, so I just told that it might be this case in the case of ideal gases. But you are pointing out the right way that if you look into it in this manner, then there has to, since you are mentioning it will imply an isothermal expansion, then we need to see how this is. It should essentially give a work done, right? PV work. But why is it is not happening? I think we need to dive a bit more. I think.
Yes, sir. Yes, sir.
Me also from my end as well. But
yes,
as per the general statements or the general knowledge, in the case of free expansion for ideal gases, this is the case. But as you are mentioning, I think we need to look into it a bit more. I think for better, I must say, understanding.
Yes, sir. Yes, sir. For sure. So by that time, I will also go into the details. Like what is the I need to check out some of the books.
Yes,
so
exactly.
By the next session, I will look into it, sir.
Yeah, sure. And if you get to know, please let us know. I think we can give you a time to make us understand that.
And sir, one special thing I would like to mention. Thank you very much for spending this much time and like discussing this issue for this longer time. And thank to all the participants.
No, it's fine.
I think
It's our job.
Abhishek Sarkar sir, right, sir? Your
Yes,
name.
yes, yes.
Yeah, yeah, yes. Thank you very much for your time, sir, and this wonderful explanation.
No, sir. Please, you also. Thanks for having this discussion. Like it's very rare that we have just detailed discussion in these sessions, but
Hmm.
I think I'm also privileged to talk, and I have like I'm just saying frankly as well. Like if you get the answer by the next session, please let every one of us know in the next session as well. You can just raise your hand or just tell me. I'll pause and you can just give us the explanation. You can even share your screen and let us know the explanation. Would that be okay?
Yes, sir. Fine, sir.
Yeah. Thank you so much.
Yeah.
Okay.
Thank you. All doubts clear from my side, sir.
Okay.
Thank you.
Thank you. Okay. Yeah. So I think this all we have done. Then remains the final topic for today's discussion. That was the pressure. Okay. So there are different properties that we've discussed till now, and pressure we'll just try to like to say discuss a bit more. And I think we won't discuss it about it in the later part of the course. But since we're discussing about pressure, so it's a good practice to understand how it is measured in real life or in say in our day-to-day life, how pressure is quantified. Okay, so it's just a basic overview. Okay, so I don't think we will I'm what to say we will discuss much more on it and the other devices that we are used to measure the pressure, but it's a good, I would say, a good way or a good practice to understand about this in the introductory session. Okay, so pressure in definition is normal force exerted by the fluid per unit area. Okay, again, if you look want to go deep into this, again there is a very thorough discussion in the fluid mechanics perspective, but for thermodynamics and for a basic topic discussion, I don't think we need to go beyond that. Okay, then there's a concept of absolute pressure and gauge pressure. So absolute pressure is basically atmospheric pressure plus the gauge pressure, or a simple equation that P absolute would be P atmospheric plus P gauge. Okay, P gauge. Okay, and there are different devices that are used to measure these pressures. This manometer, Bourdon gauge, barometer, and the device that we are concerned with in our today's discussion is the manometer. Okay, so let us just take this example. It's a simple piezometer or barometer, simple barometer in this case, which is used to say measure the atmospheric pressure. Okay, so just consider a inverted tube inserted in a liquid where the pressure exerted on the surface of the liquid is atmospheric pressure. Okay, then because of this pressure the liquid level rises inside the tube. Okay, because for it's a simple understanding, like if you push the liquid I'm sorry if you push the liquid from the surfaces, the liquid since it has nowhere else to go, it will try to go inside the tube. Okay, and it will rise to a certain height and then achieve a constant value. Given that the pressure inside this tube is vacuum or zero atmospheric pressure, then the height of the liquid that rises inside the tube would essentially give us a quantifiable way to measure the atmospheric pressure. Okay, so here in the case of this barometer, PATM would be equal to rho gh, where h is the height of the liquid inside the barometer or this tube. Okay, for example, if we know that fluid, for example, if this is mercury, in this case it can be water or anything that you want, but mercury specifically, because since density of mercury is very high, then height of the liquid that rises inside the tube is considerably small and measurable. For example, if you use a lower density liquid, for example say water or air, then the height of the liquid that it rises would be very huge and would be very difficult to be quantified. Okay, that's why I won't say quantified, very difficult to be measured. That's why a very dense liquid is used to measure the atmospheric pressure. So this is a simple equation that PATM is equal to rho gh, and this comes from the hydrostatic law, but I don't think I need to go into that for to see where this equation comes from. Okay, Then rho is 13,600 for mercury, G is 9.81, and H we need to find out, and we know atmospheric pressure is 101,325 pascals, where Pascal is the unit of measuring the pressure. Then H is given by 101,325 divided by 13,600 divided by 9.81, where G is 9.81, the acceleration due to gravity. Then H turns out to be 0.76 meter. Okay, and this H is basically termed as the barometric height, or the height of the mercury column in a piezometer that represents the atmospheric pressure. Okay, then yeah, so I think I will just directly skip to this part, this example. Okay, yeah. Consider a case where there is a flow of liquid inside this tube. Okay, inside this tube, say from here to here, and we are using a manometer to measure the to measure the pressure inside this pipe or tube. Okay, so this manometers, when you deal with it, even if say in thermodynamics, I don't think we will use it this much, but in fluid mechanics it's a very, what to say, basic or staple problem where manometers are used, how the manometers are used to measure the pressure. So if you are interested in fluid mechanics, or you are going to take fluid mechanics course, I think this will come in handy. So I will just describe you how to measure the pressure using manometer in this particular example, and I think after that all of you will be very quite well versed in dealing with this kind of problems. Okay, so in this then we will see that there are two different levels of liquid inside the manometer, where one is at a higher level compared to the another. Okay, so it's a general practice to use the lower level of liquid as your base, and we usually term it as datum in the case of fluid mechanics. So we usually term it as datum. Okay, or the base level. Okay, then what we need to do is basically balance the weight of the liquids, balance the pressure of the liquids in these two levels from the datum. Okay, say it is point A and B, so we just need to balance the pressure at point this at this particular level, because from this case, say P is equal to rho GH, where is basically the pressure obtained from the hydrostatic law, P is equal to rho GH, you will see that if rho and G are constant, okay, if rho and G are constant, then pressure is only a function of height, or H is only dependent on H. So if point A and B are on the same level, then it will imply that the pressure at point A and point B should be equal. So that's the very important concept that we need to understand. Okay, so it's from that only we can measure the or find out the pressure at this point P. Okay, then if we try to balance it, then pressure P is the one that is being imposed on this particular region A. So P would be equal to rho G Z. Rho is the density of liquid inside this column, so rho G Z, these are two different liquids. Okay, so rho G Z plus this pressure P naught. Okay, P naught basically represents your atmospheric pressure, or it represents the atmospheric pressure. Okay, we know that P naught is rho G Z naught, where Z naught is the barometric height. It was 0.76 meter, if you recall, right? From that we'll have P is equal to rho G times Z plus Z naught, where rho is mercury in this case. I think I forgot to mention that. So rho is also given. Okay, 14,600 kg per meter cube. Okay. Okay. Then if you do the calculation, you'll get that rho is 39,600, G is 9.81, and Z is 0.562. Okay, I'm sorry, Z also I need to mention. I'm sorry, I'm just forgetting the part. So it is 0.562 meter. Okay. Z is 0.562 and Z naught is 0.76 that we got from this case. Okay, this one. So if you do that, you will get that pressure is around 177 kilopascal. Okay, is this step clear? So I think in the week 1 assignment, I'm not in line with the, what to say, assignment timings. I think you might have already submitted, but if not, I think there are some questions on these manometers. So using this principle, I think you can quite do quite well in problems involving manometers. So from thermodynamics perspective, I don't think you will deal with manometers anymore in this course, but it's just a good practice to have knowledge of this kind of things, and it comes quite handy in different other subjects such as fluid mechanics. Okay, so yeah, I hope that's all from my end. Jay, you had a doubt, but yeah. Jay, okay. So yeah, it's fine. I think then if there's no, oh, it's clear now. Okay, thanks, Jay. And yeah, again also thanks to all the students and Deepak and Jen, all the students who have interacted. Thank you for making this session so interactive. And as you can see, I am also a fellow student like all of you, trying to understand the course from my end as well, and just having a discussion with all of you. You all may know a lot more things that I also don't know, but so it's a very good practice to make this session interactive so that I can also know things that I do not know. Okay, and I can also teach you things that I know, and it will be helpful for all of us. Okay, so with that, I think it's I can say this is one of the very good first session for this course. So yeah, so with that, I think we can end today's session, and let's meet next Tuesday. Okay, thank you everyone. So if there's no doubt, I think I will end the session. Okay, you all can also leave. Okay then, yeah, see you next Tuesday. Thank you everyone.